Hello, and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This video is one in a playlist on probability distributions. The playlist is planned to include a three-part series on distributions as a whole, plus individual videos on 9 different types of distributions, as well as several on the properties of distributions. As of this recording, all have been completed except for the last one on variation, variability, etc. So there are individual videos on all the probability distributions addressed in this video. See statistics from atoz.com/videos for the latest status of my videos completed and planned. In all my previous videos, we started with a list of 4 or 5 keys to understanding, which summarized on one page the most important things to know about the statistical concept. In this case, we're going to use this table instead of a list of individual keys to understanding. You can see that there are 3 major categories of distributions, and they have to do with whether the data and the distribution are continuous or discrete. This is explained in the Distributions Part 1 video and in that chapter in the book, but let's cover it again here briefly. Here is key to understanding number 3 from the Part 1 video. These graphs show the difference between a distribution that uses discrete data and has a discrete graph, which is the one on the left, compared to a distribution with continuous data and continuous curve, the one on the right. For a discrete data distribution, the values of the variable x are usually non-negative integers because they are counts. There is no probability shown for 1.5, for example, because 1.5 is not an integer, and so it is not a legitimate value for x. The probabilities for discrete data distributions are shown as separate columns. There is no space between the columns because there are no values on the horizontal axis between the individual integers. For continuous distributions, values of the horizontal axis variable are real numbers, and there are an infinite number of them between any 2 integers. So the curves are smooth and continuous. Continuous data are also called measurement data. Common examples are things that are measured, like length, weight, pressure, etc. The probabilities for continuous distributions are infinitesimal points on smooth curves. Okay, that explains the first 2 categories of distributions headed by the green boxes in our table. But what about the third, in which we can have discrete or count data and a continuous distribution? In these cases, the source of data is discrete, but subsequent calculations produce continuous numbers, and those are the numbers shown in the distribution. More on that later. Back to the top of our table. Under continuous data, continuous distribution, often we want to determine if there is a statistically significant difference between 2 means. The means could be from samples of 2 different populations or processes, or they could be a mean from a sample and a specified mean. The specified mean could be a target or a historical value or any other specified number. There are 2 choices for the distribution, a t-distribution or the normal distribution, in which z is the test statistic. But in almost all cases, you'll want to use the t-distribution. The z or normal distribution can be used only if we know the standard deviation of the populations or processes from which we are gathering data, and that is rarely the case. There is a different t-distribution for each different value of n, the sample size. Conversely, the test statistic z does not vary with sample size. For larger sample sizes, the t-distribution converges to the normal distribution. So some say that you can use z when the sample size is greater than or equal to 30. Others say greater than 100. If you have access to statistical software tables or a calculator, you're probably better off always using t. If you don't, and you just want to do a back-of-the-envelope quick estimate, you can use z if, for example, you remember that z equals 1.645 for a one-tailed test or 1.96 for a two-tailed test, in both cases when alpha is 5%. To net it out, you'll almost always use the t-test statistic and its distributions to compare two means. Use the t-distribution to compare means using one of these three tests. In the one-sample t-test, we compare the mean of a sample from a population or process to a mean that we specify. The specified mean could be a target mean, say a competitor's mean, or a historical mean, or an estimate, or any other value. In a two-sample t-test, we compare the means of samples from two different populations or processes. For example, the test results from two different products. The third type of t-test is the paired t-test. The mean of one sample of paired data is compared to the mean of another sample of the pair. The best example of this is before and after. We take the same test subjects, say call center workers, and compare their productivity before and after training. The two-sample t-test is often called the independent samples t-test, while the paired samples t-test is also called the dependent samples t-test. In our table, still under continuous data, continuous distribution, we find two distributions listed under a section called Compare Variances. If we want to compare variances from two samples, we use the F distribution and the F test. If we want to compare the variance calculated from a sample to a specified variance, then we use the chi-square distribution and the chi-square test for the variance. As with the one-sample t-test, we specify the variance. It could be a target, a historical value, or anything else. If you remember which t-test is which, that can help you distinguish these two tests for the variance. The chi-square test for the variance is analogous to the one-sample t-test. It compares the variance of one sample of data to a variance we specify. And the F distribution and the F test is used to compare the variances of two samples. As such, it is analogous to the two-sample t-tests. As with the t-tests, when we say compare, we mean that the test determines whether or not there is a statistically significant difference between the two variances. Okay, we're still talking about continuous distributions and continuous data. When we're dealing with time to an event or between events, the exponential distribution is often used. Here are the first two keys to understanding from my video on the exponential distribution. 1. Exponential distributions can be used to solve problems involving the time interval to or between events. Key number 2. Exponential distributions can be used when events occur independently and at a constant average rate. As an example, let's say we own a small shop and one new customer arrives on average about every 15 minutes. We would like to close up shop 10 minutes early today, but what is the probability that a new customer would arrive after we left, but before our normal closing time? The mean time interval between customer arrivals is 15 minutes. The exponential distribution can help us calculate the probability of a customer arriving in the 10-minute interval between the time we leave early and our usual closing time. It turns out to be 51.3%. Similar uses include time to complete a process step or time between failures. The exponential distribution can be more useful when dealing with infrequent events. If you use the Poisson distribution and count occurrences within a given time intervals, you can get a lot of zero counts and a few counts of 1 or 2. It can be better to use the exponential distribution and measure the times between the occurrences. In this next group of distributions, we want to know, given a sample of discrete or count data, what is the probability of something occurring? 3 distributions are used: the Poisson, the Hypergeometric, and the Binomial. The first thing to determine is, are we counting occurrences or units? The best way to describe the difference between units and an occurrence is with an example. Let's say that we manufacture shirts and we are expecting a sample coming off the production line. We are inspecting a sample coming off the production line. If a shirt has 1 defect, we count it as 1 defective unit. If the shirt has 3 defects, we still count it as 1 defective unit. Either way, we could not sell a shirt with any number of defects to a customer. We could also count 3 occurrences of defects on that 1 shirt. This would give us more complete information on the overall quality of our manufacturing process than just counting 1 defective shirt. If we count occurrences, we use the Poisson distribution. If we are counting units, then there are 2 possibilities. If we sample without replacement, we would use the hypergeometric distribution. If we sample with replacement, then we can use the binomial distribution if the following criteria for a binomial experiment are also met. These include: 1, there are a fixed number n of trials; 2, each trial can have only 1 of 2 outcomes, yes or no; and 3, the probability p of a yes in each trial is the same for all trials. For more on the concept of sampling with or without replacement, see the video on the binomial distribution. With these 3 cases, we start with discrete or count data, but the distribution we use is continuous. That is because we convert discrete count data to something else before using the probability distribution to calculate the probabilities. There are 3 commonly used chi-square tests. Earlier, we described the chi-square test for the variance, and in an upcoming slide, we'll discuss the chi-square test for independence. Here, we're talking about the chi-square test for goodness of fit. There is a separate chapter in the book on this test, and there will be a separate video. So we'll just cover it briefly here. As an example, let's say we're about to open a new bar, and we want to plan staffing levels. We know from past experience that the number of customers varies by day of the week. We don't know how many customers to expect in a week, but we can estimate what percentages to expect each day. The observed count for each day is shown. This is after we took a sample for 1 week. The weekly total is 765. If we multiply the weekly total by each of the daily expected percentages, we get the expected frequencies. These are not integer counts. We can't tell by just eyeballing these numbers whether or not there is a good fit between our expected frequencies and the actual observed counts. However, the chi-square test for the goodness of fit does do this. Similarly, with the chi-square test for independence, we can start out with counts as shown here, but the test converts them to proportions before doing the comparison in the test. Here we are testing whether there is a statistically significant difference between females and males in their favorite type of fruit juice. The data shown here are actually counts, but we are comparing 100 females with 200 males, so we are actually comparing proportions or percentages. Again, more on this in the book article or the video, upcoming video on the chi-square test for independence. And a two-tailed z-test for 2 population proportions is statistically the same as a chi-square test for independent using a 2x2 table, which is 2 populations and 2 proportions. Okay, that concludes our clarification of the concept of which distribution to use when. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60 plus concepts in the book if folks like you tell me that more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you'll find interesting, like a statistics tip of the week series, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page, Statistics from A to Z, and on Twitter as @StatsA to Z.